It was an age when our planet was very different, a time when most of the landmass was bunched up in a giant supercontinent called Rodinia, a time when the atmosphere had a lot less oxygen in it than today, and when life was still trying to make the leap onto land. It was also the time when some of Earth's largest volcanic eruptions ever occurred. These eruptions unleashed over 1 million cubic kilometers of ash and lava and created calderas so large they are now known as supercalderas. So what could have caused such catastrophically enormous explosions? Did these ancient eruptions have something to do with the formation of our moon? Let's dig into the science to find out. Hi, I'm here, and this is my channel. The two oldest and two largest known supervolcanic eruptions on Earth took place during the Paleoproterozoic era between 2500 and 1600 million years ago. But although we know that these eruptions were major game changers for life on Earth, we don't know exactly why they happened. The earliest known supereruption was the 2.5 billion-year-old Onverwoud event in present-day South Africa. Its massive caldera is about 450 by 300 kilometers across. Then there's the 2.1 billion-year-old Rurutu complex in present-day Australia. This eruption covered an even larger area. The main caldera is around 600 kilometers wide, and nearby satellite calderas extend the overall footprint to nearly 1,500 square kilometers. And then there's the 1850 Toba event in Indonesia, which needs no introduction, because you've heard about it before. Finally, there's the 1,200 million-year-old paint pot complex in New Zealand. And while its initial eruption was smaller than the others, it went through multiple eruption cycles, and its caldera grew to become the largest of them all at a whopping 700 square kilometers. We know that each of these supereruptions happened within a few million years of a major change to the global climate. But whether the eruptions caused those changes or were caused by them is still up for debate. So what do we mean by major climatic changes? We mean shifts from a warmer to a colder climate or vice versa. For example, the Onverwoud event happened right after the Great Oxidation event, a period when the amount of oxygen in the atmosphere suddenly increased, possibly due to the evolution of photosynthetic bacteria. But it could also be that the eruption itself caused that increase in oxygen by releasing gases trapped deep underground and bringing them to the surface. Similarly, the Rurutu eruption took place just before the first known ice age on Earth, but it's unclear if the eruption caused the cooling or was caused by it. Some scientists think that large eruptions might have played a role in triggering snowball Earth events, but that's unlikely given that their frequency does not line up with the timing of major climatic shifts. Instead, major climatic shifts may have been triggered by plate tectonics. As the supercontinents broke apart, new ocean basins formed, which reduced the amount of carbon dioxide in the atmosphere. This would cause the global temperature to cool until more CO2 could be released from volcanic activity or by chemical reactions in the ocean. Now you might be wondering, how big are we talking? How much carbon dioxide do you need to warm up or cool down the entire planet? Well, according to one study published in 2023, you only need to remove or add about 1% of the total amount of carbon stored in rocks and sediments at the Earth's surface. In the case of the breakup of Rodinia, researchers estimate that the removal of 1% of that carbon could have led to a 10 degrees Celsius drop in global temperatures. In other words, this is how our planet can go from an ice cube to a hot tub with just a tiny change in carbon levels. But if the climate was already cold enough to form ice sheets, how could the eruptions have melted them? Well, think about it this way. While the eruptions themselves might not have been hot enough to melt ice, they may have brought heat from deep inside the Earth to the surface, thus warming the planet and melting the ice. Here's what I mean. While the outer layer of the Earth, the crust, is quite cool compared to the rest of the planet, it's still hot enough to melt rock, especially if it's brought up from depth by a volcanic eruption. For example, the magma that produced the lavas of the 2010 eruption of Mount Eyjafjallajökull in Iceland came from depths of 30 to 40 kilometers below the surface. That magma had temperatures ranging from 1050 to 1200 degrees Celsius. Magma from deeper depths can be even hotter. And while it's true that the Toba eruption didn't cause a runaway greenhouse effect, the magma reached temperatures of around 1500 degrees Celsius, which is about 2700 degrees Fahrenheit. So yeah, that's definitely hot enough to melt ice. But wait, hold on. Scientists estimate that the mantle wedge, the part of the Earth's mantle that sits directly beneath continental crust, has temperatures of roughly 900 degrees Celsius or 1650 degrees Fahrenheit. If so, how did the eruptions bring heat to the surface without melting the crust on the way up? Well, that's where the chemistry comes in. Even though magma from deeper depths is hotter than magma from shallower depths, it's not necessarily the higher temperature that causes melting. It's also the lower pressure. When magma is deep underground, the high pressure keeps it from melting, even if it's very hot. For example, Mount Vesuvius erupted twice in the past. Once in 79 AD, which buried the Roman city of Pompeii under ash, and again in 1631. In both cases, the eruption was explosive, but the 1631 eruption was much more violent. Why? Because in 1631, the magma chamber was filled with gas, and that gas was under much higher pressure than the magma chamber that blew up in 79 AD. This means that even though the magma in 1631 was not hotter, it had more energy and caused a much more violent eruption. In other words, the energy in magma is a combination of its temperature and its pressure. And while hotter magma has more energy, lower pressure also adds to the total amount of energy. To understand what's happening to magma as it rises, imagine putting a lid on a pot of boiling water and then taking the lid off. The water will start boiling vigorously. That's because the air pressure outside of the pot is lower than the pressure inside the pot, pushing the water to expand and boil vigorously. But if you put a lid back on the pot, the water will boil gently because the air pressure is now equal to the pressure inside the pot. Similarly, as magma rises, it experiences lower and lower pressure, and if it's hot enough, it will start boiling, releasing gases that were previously dissolved in it. Now, if you remember what happens when magma reaches Earth's surface, this should tell you what happens next. That's right, they explode. The sudden release of gas creates an enormous amount of pressure that blasts the magma violently upwards and forms giant ash clouds that can reach the stratosphere and even the mesosphere. So yes, the magma generated by these ancient supereruptions was likely hot enough to melt ice, but they would have needed to be even more explosive than they were to melt the entire planet. But perhaps it wasn't the heat that mattered, but the debris. During a large volcanic eruption, trillions of tons of dust and gas get blasted into the atmosphere. In fact, the 1815 eruption of Mount Tambora in Indonesia ejected 50 billion tons of sulfur dioxide into the atmosphere. While that might sound like a lot, it's nothing compared to the 2.8 trillion tons of sulfur dioxide released by the 1991 eruption of Mount Pinatubo in the Philippines. Imagine how much more material is ejected during a supervolcanic eruption. All that material can block sunlight and cause global cooling. For example, the 1816 eruption of Mount Tambora lowered the global average temperature by 2 degrees Celsius and caused the year without summer. In 1817, the Northern Hemisphere experienced record low temperatures and widespread crop failures. And yet, the Mount Tambora eruption was 30 times smaller than the Toba eruption. It would seem that the Toba eruption alone should have been enough to freeze the entire planet, but it wasn't. Instead, it kicked off a chain reaction of eruptions. Within a few 100,000 years, hundreds of large eruptions occurred all around the world, leading to the formation of the Deccan Traps, a region of layered solidified lava in present-day India. But whether that chain reaction was a response to the Toba eruption or the two events were unrelated is still debated by scientists. What is not debated is that there were a lot of consequences. According to one study, the intense volcanic activity associated with the Deccan Traps caused a mass extinction event that wiped out 70 to 90% of marine species and 80 to 90% of terrestrial vertebrate species. Another study claims that the Deccan eruptions alone were responsible for an ice age that lasted for 100,000 years, and yet life found a way to survive. But if these eruptions caused such dramatic changes, Why haven't we seen anything similar since? One reason is that supercontinents like Rodinia tend to break apart every 400 million years or so, and that hasn't happened in a long time. In fact, the supercontinent cycle may have come to an end with Pangaea, the last supercontinent. So it may be that we won't see another Rodinia-like supercontinent for hundreds of millions of years, but there is another possibility. Perhaps the conditions for massive volcanic activity no longer exist. Most of the gigantic eruptions occurred in areas where the Earth's crust was slowly being pulled apart, allowing magma to rise and create new ocean basins. But the new oceans formed after the breakup of Rodinia were quickly recycled back into the mantle, leaving behind thickened continental crusts that act as lids preventing future eruptions. These days, most volcanic activity occurs along subduction zones, where one tectonic plate collides with another and is pushed beneath it. In fact, the Mariana Islands, Japan and the Eurasian Islands were all created by subduction zone volcanism. The thing is, subduction zones don't produce the kind of massive eruptions that created the ancient supercalderas. So if there's no more Rodinia and no more magma chambers beneath thick continental crusts, we may never see a repeat of the supereruptions that shook our planet millions of years ago. Unless we trigger one ourselves, our chances of causing a supereruption today are slim to none. But if we keep digging deep holes for geothermal energy, we might accidentally tap into magma chambers we didn't even know existed. If you want to know more about the challenges of harvesting energy from the Earth's core, you can watch this video right here. Thanks for watching. If you enjoyed this video, make sure to subscribe and click the like button. And if you have any suggestions for topics that I should cover in the future, please leave them in the comments section. I'll see you next time.